So now we are going to talk about addition of vectors and their geometrical representation. Okay. So given two vectors A, which is a1 comma a2 comma a3, and b, which is b1 comma b2 comma b3, their addition is defined as a plus b is equal to a1 plus b1, a2 plus b2, and a3 plus b3. So again we are adding them component wise. So geometrically this addition means the following. So if you look at this picture, so you have x coordinate, y coordinate, and z coordinate, and suppose you are given two vectors a and b. You complete the parallelogram whose adjacent sides are given by these vectors a and b. So this is the parallelogram that you see here. So now you look at the diagonal which starts from the origin 0, 0, 0. So this diagonal of the parallelogram, the vector that it describes, which I have drawn here, is nothing but a plus b, the addition. So let us repeat again. You look at any two vectors, you complete the parallelogram, and the diagonal, which is this diagonal, which starts at the origin, which is also the starting point of the vectors a and b, is nothing but the vector a plus b. So we will look at a proof of this. So by a proof we mean that the coordinates of this point where this vector a plus b ends is nothing but this a1 plus b1, a2 plus b2, a3 plus b3. So this is what you will see in the tutorial. So this is a pictorial proof of vector addition in R2 where the third component is dropped. I will skip it here. We will discuss it in the tutorial. Okay. Now you can visualize vector addition in a different way. So now let us look at this picture on the left where you have these vectors a and b starting at the origin. So earlier we were drawing a parallelogram, right? And we are looking at a plus b as the diagonal, as the certain diagonal of this parallelogram. But now I am going to draw a triangle. So what we will do is, we will translate this vector b so that its starting point is same as the ending point of A. So earlier a vector is described as something that begins at the origin. Now what we are doing is we are translating this B to here where the starting point of B is nothing but the ending point of A. Okay. So you have A and then B. So now these are two sides of triangle. So you complete this triangle. Okay. When you complete this triangle where the starting point is the origin and the ending point is now the new ending point of B, this vector is nothing but A plus B. So this is visualizing vector addition using triangles. Earlier we were using parallelograms. Now there is also a possibility that these A and B, when you do this, they come out in a straight line, right? Like this. So suppose you translate B and it so happens that A and B are in the same line, then you don't get a triangle, but the final vector that you get, whose starting point is origin and ending point is the new ending point of B, is the vector A plus B. Okay, so this is easy to see. Now here, if we, so as I said in the tutorial, we will talk about the proof. Okay, so this is another way in which you can visualize vector addition, and this visualization is quite useful. So let us repeat what we did. To add two vectors A and B, translate the vector b so that its initial point is same as the terminal point of the vector a. Then complete the triangle with two sides given by the vectors a and b. The third side of this triangle is the vector a plus b. Okay. Now let us understand geometrical representation of scalar multiplication of a vector. So given a vector a and a scalar alpha, which is a real number, alpha a is given by alpha a1, alpha a2, alpha a3. Okay. So what does it mean? I have drawn several pictures here. So let us say your initial vector is this vector a. Okay. So what is 2 times a? 2 times a is nothing but multiplying each component by 2. What will it do? It will stretch or it will scale this vector by twice, right? So whatever is the original length, it will become twice of that. Okay. Now, if you multiply by minus sign, then the direction is reversed. Okay. Initially, it was going in the front. Now it goes in the back. If you multiply by 1/4, then the length is shortened, right? Again, minus 1/4, it's shortened and in the reverse direction. 3 by 2a, it's again scaled in the same direction. Okay, so what is the upshot? If you multiply by a positive real number, it gets scaled by the same amount in the same direction. If you multiply by a negative real number, it gets scaled by a certain magnitude in the negative direction. Okay. All right. So now let us look at geometrical representation of vector subtraction. Okay. So if you are given two vectors a and b, by um, by vector subtraction, you can see that a, so you can think of minus a as scalar multiplication of a by minus 1, right? So b minus a is what? B plus minus a, right? So when you do a plus b minus a, you get b, right? So if you assume the vector addition definition and vector and scalar multiplication definition that we saw, then you have this picture, right? So suppose you take these two vectors a and b and you want to see what b minus a is, right? So what is b minus a? So, so what is b? B is when you add a and b minus a, right? So that means b should be, if you use the parallelogram geometric representation, then this b should be the diagonal of a certain parallelogram whose adjacent sides are what? A and b minus a. So now one of the sides is already given to you, which is a. This is the diagonal. So you complete the parallelogram. Okay. So when you complete this parallelogram, this side which touches the origin is nothing but b minus a, right? Because the sum of a and b minus a should be b. That's using parallelogram. But using triangle version of visualization, you are given vectors a and b minus a, right? What should be b minus a? It should be nothing but a vector which is the third side of the triangle whose sides are a and b, right? Remember we had a and a vector b. We translated b so that it starts with the end point of a and then we completed the triangle. So it's the same thing here. You have a and then you have b minus a. Their sum should be b. So that's how b minus a is described. Okay. So this can be seen using both parallelogram picture and the triangle picture. Okay. So now, so far we defined a vector which starts at origin and we were translating it to for various geometrical representations. So now let us define a vector in general which need not start at the origin. So you can define vector joining two points. So suppose you have two points P and P prime, and what is a vector joining P and P prime? It's geometrically described as this line segment with an arrow describing what is the starting point and what is the ending point. So suppose the points are A1, A2, A3 and B1, B2, B3. A vector joining points P and P prime with tail P, so this is called the tail where you start, and head, this should be P prime, I'm sorry about that, and head P prime is described as follows. It is denoted as PP prime with an arrow on the top, and it's written as B1 minus A1, B2 minus A2, B3 minus A3. How do you get this? So if the head is P and tail is P prime, you take B1 minus A1, B2 minus A2, B3 minus A3. Okay, and this representation is not arbitrary. We will discuss this more in the tutorial session. There is a reason why it's this, why this vector is described like this. Okay. So you should know triangular brackets here because this is a vector. Okay. Now this B1 minus A1, B2 minus A2, B3 minus A3 are called the components of this vector. And if you look at the vectors 1, 0, 0, which is denoted as I, 0, 1, 0, which is denoted as J, and 0, 0, 1, which is denoted as K, they form a basis for R3. And these vectors are called standard basis vectors. And using vector addition, if you have any vector, vector addition and scalar multiplication, if you have any vector v1, v2, v3, it can be written as v1 times 1, 0, 0 plus v2 times 0, 1, 0 plus v3 times 0, 1, 0, 1. Now how do you get this? So if you multiply v1 by this, you get v1 0, 0, 0 v2 0, 0, 0 v3, and when you add them, you add component wise and you get v1, v2, v3. So this can be written as v1i plus v2j plus v3k. So any vector can be written as in this form, okay, where I, j and k are the standard notation. We are not going to change this notation anywhere in this course. In fact, they are standard notations used in all the books that you will see. Okay, these are called standard basis vectors. So any vector can be represented uniquely in terms of these standard basis vectors like this. Okay. So what is the geometrical representation of standard basis vectors? So if you look at the I vector, which is 1, 0, 0, it is nothing but the vector which starts at the origin and ends at the point 1, 0, 0, which is on the positive x-axis. The vector j, which is 0, 1, 0, is the vector starting at origin and ending at 0, 1, 0, which is on the positive y-axis. Similarly, you have k, which is 0, 0, 1, which is the vector starting at origin and ending at the point 0, 0, 1. Okay, so these are standard basis vectors. And let us look at the representation of this vector 2, 3, 2 which is what? Which is the vector starting at the origin and ending at the point 2, 3, 2 in terms of standard basis vectors. So how do you write them down? So you know that this 2, 3, 2, what do they represent, right? They are nothing but distances from origin in the positive x-axis, in this case, positive y-axis, positive z-axis. So what is 2i? 2i is nothing but this vector, right? What is 3j? 3j is nothing but this vector, which is when you drop the perpendicular and you look at the distance. 2k is this. So you have the same direction as I but scaled by 2. You have the same direction as j but scaled by 3. Same direction as k but scaled by 2. So let us look at a few examples. The first one is find the vector v from the point 1, 1, 1 to the point -1, 0, 4. So let p be 1, 1, 1 and p prime be -1, 0, 4. Then the vector v is given by -1, which is the first coordinate of the tail, minus minus 1. So minus 1, 0 minus 1. Third is 4 minus 1, which gives you -2, -1, 3. And if the vector v from the point this to the point p prime is given by this, you have to find the point p prime. So you assume that the point p prime is x, y, z. Then x minus 1 should be the first component of the vector. Y minus 1, which is y plus 1, should be the second component of the vector, and z minus 3 should be the third component of the vector. When you solve these three equations, you get the point to be 1, -1 and 8. Okay, so let us stop here.